Hello there, welcome back to another video from Gaurav Tutorials. In this video, we will discuss about growth rates. But first, let us have a brief recall of what we studied in the last class. In the last class, we discussed about phases of growth, whereby we understood and we discussed that there are different phases of the growth. First of them is meristematic, followed by the elongation and the maturation phase. In the meristematic phase, we discussed the fact that meristematic phase is also referred to as formative phase of the growth, during which the cells of meristem will divide and add new cells. We discussed about the characteristics of the meristematic cells. Also, these newly formed cells in the by the activity of the meristematic tissues or cells will enter into the phase of elongation, during which they would accumulate protoplasm and increase in size. All right, we discussed about two theories that are that can be considered for the development of the cell wall. First of them was intussusception and the second was apposition. Then once the cell have achieved enough protoplasm, accumulated enough protoplasm and has grown sufficiently, would enter into the phase of maturation, whereby it will differentiate itself and take up a fixed form and function. When it takes up the fixed form, it is referred to as a structural differentiation, and when it takes up the fixed function, a specialized function, it is called as a physiological differentiation. So now come back to the topic and let's have a discussion on growth rates. Let's take one example and try to understand what is this growth rate. Okay, so you observe this leaf, and you find it has a certain dimension. Okay, after some time, maybe a day or two, we find there is a considerable increase in the size of the plant. Okay, so since there is an increase in the size of the plant, can I say that the growth has taken place? Yes, I can say, since there is an increase in the size of the plant, and this increase in the size of the plant is measurable, I can say that the growth has taken place. But while growing, the plant did consume some of our time. Okay, so this growth per unit time is referred to as growth rate. Okay, so increase in the growth per unit time is referred to as growth rate, and there are two types of growth rates that are observed. There are two types of growth patterns that are observed in case of the plant. First of them is an arithmetic growth, and the second one is a geometric growth. So now let us take an example and understand what is arithmetic growth, okay, or arithmetic growth model. So we have got a meristematic cell. Okay, it will divide to form two cells. Okay, now the two cells that are formed here, of these two cells, one of the cell will get differentiated. Okay, one of the cell gets differentiated and loses its ability to divide. However, the other cell, as there are two cells formed here, the other cell will not lose its ability to divide and will divide again. So you have two cells formed once more. This cell, one of these two daughter cells that are formed, will remain as meristem and would not lose its ability to divide. It would divide again and form two daughter cells. The other cell which was formed here would again lose its ability and form and undergo differentiation. All right, so you have got this cell also entering this cycle. You have got three cells. All right, now these two cells which are formed here, would one of these two cells would again lose its ability and become differentiated and take up a fixed shape and a form. Right, this cell on the other hand will not divide. I mean, it will not take up the differentiation, it will not undergo the differentiation process, but would remain as meristem. So such a model of growth where one of the cell divides and the other cell takes up the differentiation and becomes specialized with respect to its form and function is referred to as an arithmetic growth model. Okay, so here the rate of growth is constant. Okay, the growth rate here is constant. The growth rate in this case is constant. Okay, and it occurs in arithmetic progression. Excuse me. It occurs in arithmetic progression. And generally what do we find is after mitosis, one of the cell, okay, one of the cell continues to divide, whereas the other cell, excuse me, yeah, other cell differentiates and takes up fixed form and function, right? So this kind of growth, that is arithmetic growth, is generally seen in the root. Okay, it is seen generally in the root. The elongation of the root occurs at a constant rate, right? The root elongation at constant rate. Now we can actually take a few scenarios and understand how does this process of arithmetic growth works at constant rate. Let me finish this first. A constant rate, right? So let's take up a scenario. Whereby you have got let's say at time t, you have let the time be 0. You have got the number of cells as 5. Okay, after time, let's say 2 hours. Okay, in fact let's put it 3 hours. Okay, after 3 hours we find that the number of cells, just a minute, yeah, number of cells here are 20. Okay, so what has happened? Can you understand what has happened? Yeah, let's take this thing and do it in a in a mathematical form. Okay, so you have got 5 cells. When the time was 0. Okay, now after 3 hours you find how many cells are there in the system? There are 20 cells. Okay, the total number of cells here, boys and girls, the total cells here are 20. But how many new cells are added to the system? Yeah, 15 cells. You already had 5 cells at the beginning. Now the total number of cells are 20. So what are you going to do? You're going to do this as 20 minus 5 and you'll get 15 cells. Now these 15 cells took 3 hours to grow. So can I find how many cells did we get per hour? Can that be found? Can that be calculated? Here, what you will do is 15 by 3 and you get 5 cells per hour. You get 5 cells per hour. All right. Now, similar to this, if we know that 5 cells are being added every hour, can we find that how many cells will be present in the system after, let's say 20 hours? Can we find how many cells will be added to this system after 20 hours? We do know that 5 cells are added into the system per hour. So what we can do is 20 into, in fact 5 cells into 20 hours, and the initial number of cells that we had in the system was 5. So 5 into 20 times becomes 100, and then you get 105 cells after 20 hours. Right? Let's take one more scenario and then we'll try to see if there is any mathematical relation or a mathematical formula that we can come across by using by the help of these problems. So again, let the time be 0 and let the number of cells at time 0 be let's make them 15. Okay, after time at t being 2 hours, the total number of cells in the medium was let's make it it won't be fine. Let's make it 75. Let's make it 75 cells. All right. So I need you to understand, initially this medium had 15 cells at t being 0. After 2 hours, the number of cells in this medium became 75. So how many number of cells have been like how many cells have been added in 2 hours? You already had 15. Now the total number of cells have become 75. So in 2 hours, how many cells would have been added? 75 minus 15, you get 60 cells. That is in 2 hours. So 1 hour, how many cells you will be finding into the medium? In 1 hour, how many cells would have been added? So what you will do is 60 by 2 and you get 30 cells per hour. 30 cells per hour. So now, can you find number of cells after, let's say after 10 hours? Can that be done? After 10 hours, what will be the number of cells here? Yeah. Yes, we can do that. So if we had 30 cells per hour, how many cells are we going to have after 10 hours? And initially in the medium, we did have how many cells? We had 15 cells. So what we're going to do is 30 times 10, it becomes 300, and then plus 15, 315 cells after 10 hours. Right. Now, this is the number of cells after 10 hours. This one is the number of cells after 20 hours. So what we can do is we can come up with the mathematical relation that NT means number of cells after time t is equal to N0, number of cells at time 0 plus R. What we have done here is we have found rate of growth. Rate of growth means number of cells added into the medium per unit time. That means 1 hour. So NT is equal to N0 plus RT. This is the mathematical relation for arithmetic growth. Instead of NT, you can if you'll follow your book, the book says LT is equal to L0 plus R into T. And if you were to plot a mathematical form or represent this thing in a graphical form, let's draw a graphical form of this thing. You've got a x-axis here, then you have a y-axis. On the x-axis, we are going to plot, let's say we are going to plot time, and on the y-axis we are going to plot number of cells. Okay, let's take this example, this one. Okay, number of cells being 15. All right, at time 0. So let's begin with this thing. You have got 1 hour, this is 2, this is 3, that's 4, that's 5, that's 6, and 7, and 8, and then 9, and then 10. Okay, this becomes 5, 10, 15, 20, 25, 30, 35, 40, 45, 50. Okay, I'll have to extend this thing. 55, 60, 65, 70, and then 75. All right. I mean, it has exceeded beyond my expectations. All right. At time 0, you had 15 cells. Okay. You had 15 cells here. Okay. All right. What I've done is, yeah. So, how many cells are we adding every hour? How many cells are we adding after every hour? Yes. Yes. We're adding 30 cells after every hour. So, at 2 hours, how many cells did we have? At 2 hours, how many cells did we have? We had 75 cells. Okay, now. Okay. जयश्री मैंने ब्लेंडर मचा दिया.